So the things are not needed.
Huh? No, it's not needed. Oh, hello.
Okay, so generate I will invite you. Did I answer your question?
Scroll down. Let's be welcome next. We'll be talking about the challenges with the open source driver for the Nvidia.
I think I didn't hear you. Hello, everybody. My name is Karol Herbst. I'm mainly working on the Nouveau driver these days, and I wanted to tell you a little bit about what we do and what we achieved in the past and how we do stuff, and like maybe you're interested in helping out in the future, and that's kind of my hope. So first I try to introduce myself. I have like no backend for graphics development at all before starting to work on Nouveau. So I was just a normal Java backend middleware developer, had like no experience in embedded hardware. Thought it's like it's a good idea to have like an open source driver on your laptop or your machine if you're using like a GPU, because usually a lot of sensitive information is going through your display and maybe passwords are displayed and so on. And I think it's a good idea to have an open source driver for this and to be actually let you know what it's doing and so on. So I was looking into using Nouveau on my laptop, and I found quite a few bugs, and I started to fix them. And then like 2 years later, I just joined the Red Hat graphics team to work like full time on Nouveau. And just tell you this to make quite a point here, because I had no experience with this, and it's like just my motivation that brought me here, and I think you can do the same thing if you're interested. So what's like the main motivation we have in the project itself? A lot of people are just, or like, no, this is about what's my motivation here. I want to get you interested in like, if you are using Nouveau, it might be that you do this without knowing. I mean, who of you has a Nvidia GPU and is not using the Nvidia driver? So yeah, you might are already using it without knowing it. And what the second point is, I kind of want to demystify what we are doing, because we have a lot of users joining our IRC channel and are saying, yeah, it's awesome what you do, but I get like nothing how you do it, and I understand like nothing at all. And I just want to bring you a little bit closer to what we do, and maybe you get a little bit of understanding and might be actually able to help with a little bugs. Or I'm quite sure that some of you using Nouveau have a few issues and bugs here and there, and yeah, it's currently a little bit difficult for us because we are really lacking developers, and we can't like fix all the bugs. And I think it's quite sad for the users, because they actually want to and use it, and we can't. And so it's kind of why I want to give this talk. And what's also I mean, is anybody of you doing SoC development or reverse engineering? Oh, a few, okay. Because we have quite a tool to kind of document the actual parts of the like the devices, and it might be a good idea to kind of try to share those tools and to have like a common database where all the hardware could be documented, for example. So that's also what we could. So I've prepared a few topics I want to talk about, like the goals of the Nouveau project in general, some facts, what kind of reverse engineering we do, what we do for developing on what we are coding stuff. Relationship with Nvidia is also a kind of big point, because with recent hardware, we kind of need the help for signed firmware stuff, because we can't run our own code on certain parts of the GPU. We also have like what we currently want to get solved, or what is our biggest challenges so far, or the current ones, and how you could, for example, help if I could. Or I'm able to wake some interest in you. And how I would like to hold the talk is that I want to give you the opportunity to ask questions all the time. So if you're like, I talk about a topic and you have some questions or maybe even unrelated stuff, and after I finish with the topic, then it would be nice, or I think it would be good if you could just ask the questions. So do you have already like a questions or a preference what I should talk about? Otherwise, I just move forward. Okay. So for the project member of the Nouveau project, it's one of the most important goal is to understand the hardware. GPU are usually quite complex, kind of embedded devices. They have lots of parts, and there's a lot of stuff to figure out and how they work. And especially for the Nvidia GPUs, there's like no documentation at all. So it's kind of, I always see it like a kind of puzzle you want to solve. So there are like a lot of pieces, some you know, some you don't know, and you try to make a bigger picture out of all the stuff you know. It's also important to have an alternative to the closed source driver. As I already said, yeah, so that's one of the goals. We also have some researchers working for the Nouveau project who are like interested in general compute stuff, and they want to get also better understanding on how to like write better code or have a better understanding of the hardware they are working with. And with the Nvidia driver, they can't do this because they can't change the code of the driver. So they're usually doing like some research project based on Nouveau and trying out different things and see how the GPU is behaving and what's the change in the runtime. And of course, in the end, everybody of us want to have fun. So nobody really gets paid except like me and another developer. But I worked on Nouveau for 2 years now, and it was always in my spare time. And it's a fun project, so it's one of the most important bits, I would say. So some quick facts. It's MIT licensed, which is a little bit weird because most of the kernel stuff in Linux is GPL. But it's actually a good thing that the graphics stack is completely MIT licensed, because if you're thinking about BSD systems or so, they can't really include GPL software. And it would be painful for them to just like have to write all the code again just to not use the Nvidia binary. So yeah, that's the reason for this. It started around 2005, where I think Nvidia put up some open source code for the X part, but it was like not readable at all. It was like hidden everything, and it wasn't like real open source, just code with a lot of constants and kind of didn't give anything away. So there was like the motivation to do like proper open source code and have a better, like nicer way of doing open source. It was like accepted a few years later, marked stable, quite like, yeah, Linux 3.4 is already kind of old, but still it's not like in the old days. Some BSD ports, I think NetBSD has an official version already. There are some FreeBSD guys, I think, working on it. I'm not quite sure. Usually nobody of us takes or like looks what they're doing, but sometimes in the news there's like, oh yeah, a new version got spotted and stuff like this. So. And most of the Nvidia GPUs are actually supported. Like the Weaver TNT is like one of the first Nvidia GPUs, and then we are supporting up to the newest one. I'm not quite sure if we support Volta yet, but it's like the, yeah, question.
Is there any reason not to use this right now? Is there any big chunk missing, like power management? Or?
So the question is there a reason not to use Nouveau? First off, you don't get vendor support. Yeah, that's a big thing for, like, imagine you're doing like machine learning stuff, and like you have a business model behind it. So you really want to have somebody to be there to fix your problems and so on. Second problem is performance. The user space, like most of the issues are either like reclocking, so we can't really set the states for most GPUs, we can't really do this. There are some generations we support it on, like the Kepler generation and Tesla. That's, I think, if you're aware of the model names, it's like 9,000 to 200 series and 600 to 700 or something. Basic idea. So on those we can like change the performance states, but on the other ones we can't. And that's a big problem, because if you're like wanting to have a fast GPU, you buy it for a reason. So you also want to have a driver which is able to actually do this kind of stuff. And it's one of the more complicated parts in the power management to do all the reclocking. So it's taking up quite some time, and we are working on this. But with the recent generation of GPUs, like for the Maxwell one, which are like the 900 series, they actually require signed firmware to be able to change the fan speeds. So we could reclock, but then the GPU would like overheat. So we can't do this. And on the more newer generation, it's really locked down. So even if we would know how to do it, we can't. So this is like reason for the performance. And of course, in the user space, we have also like, we don't really know what's like the fast path on the GPU to do stuff the fast way. And so we have to try things out. And we are currently more like focusing on hardware support than on getting speed on, because most of the Nouveau users are quite happy if already the display is working, and then they can like attach external screens, and like for the on laptops, the GPU is powering off to increase the battery lifetime and so on. So it's kind of question of focus. Yeah. Other questions? Okay.
What is the state of the support, like feature like audio or coding?
Excuse me again?
Feature like audio or coding.
Also, the features we currently support. I will get to this. So, yeah. I think would be even the next slide. Yeah, it's the next slide. So, it's like overview of the features we currently support. Does anybody does not know what OpenGL is? Looks good. Okay. So, yeah, we are like, really.
I don't know what it's doing inside.
Yeah, but I mean, it's not important for this. So, but if you know for what OpenGL is used, it's fine by me. So, yeah, we support officially OpenGL up to 4.3. The reason why we like can't declare like 4.5 is that there's a conformance test suite from Kronos, and there's some trademark stuff behind it. So if you would like expose 4.5, there's a chance that we could like get sued due to trademark stuff. So we don't do this, just to be on the safe side. There's also OpenGL ES for like embedded devices. Like we also support those Tegra SoCs shipped by or sold by Nvidia. So there's usually on those, but you can also use OpenGL on those. It's just to support both. I think there's some layout screw up because it should be, yeah, ignore those YMC and volleyball stuff because it's a few lines below. So, oh, yeah, the entire slide is messed up. Okay. I don't know how this happened. On my machine, it was fine. So, we also support D3, D9, which is used with DirectX 9. Through like this Gallium 9 and Wine. There are some patches, maybe you've heard of it, maybe not. It's basically there to get like better speed if you're gaming through Wine. Like if you have some DirectX 9 games, you want to play them on Linux, usually do this through Wine. And there were some people working on this, and it gives like most of the time better speed and better compatibility. So there's more graphics effects and stuff like this. Then we also like support video acceleration through the two interfaces, XYMC and Pro. Those the one is old, the newest was made up by Nvidia. It's basically used for accelerated video playback. So if you have watching a video in your browser and you have an Nvidia GPU, it could like accelerate the playback so that your CPU isn't.
Also encoding.
Yeah, it's encoding isn't like supported.
Oh.
And it's not through those interfaces as well. So you have like Nvidia has the NV encoding API for this.
When I used FFmpeg last time, to encoding 1.5 hour DVD movie using i7 took something like 5 times more than using 1050 encoding.
So the comment was that with FFmpeg, it took quite a lot of time to encode something with the CPU. Yeah, there is for this NVIDIA interface, there's actually a backend in FFmpeg. It can use the GPU, and it's usually, if you're doing H.264 encoding, I'm not quite sure about 265, but it's usually 5 to 10 times as fast as the video. So for like 200 minutes video, you usually need like 20 minutes of encoding. So yeah, we would like to support this, but lack of developers and no time. So it's on a to-do list. We also support like some basic from the HWMon interface. It's an interface to get like temperature information from your device. You usually see it with the CPUs or like fan speeds for the fan and stuff like this. We currently use it to also report like voltages and some internal information about the GPU, which some people care about. It was no effort to support it, but it's like nice to say. Various power management features are like stuff like reclocking, memory reclocking, engine reclocking. There's also like shutting down the GPU when it's not used. There's also like currently somebody is working on clock gating. This basically means if your GPU is powered on, but you don't need some parts, you can just turn the parts off to save some power. So it's like, yeah, we are working on this. And what is a big point is that not all the features are actually supported on all the GPUs. So if there's like a new generation, it might be that some things are different on the newer one. So they have to be reverse engineered again and figured out and write new code for this. Yeah.
Are there any plans to support Vulkan?
The question was, is there any plan to support Vulkan? Yes, there is. I don't want to give an estimation for this, but it might happen that there will be something this year. So, yeah. Okay, and a point I want to try to make here, it's not a toy project. It's sometimes, like if there's like news for Nouveau, there's always like this kind of users who are saying, yeah, why do you do this? It's like garbage and stuff like this. So I want to make it clear that it's really stuff and it really works. So you can like play the most of the modern games with Nouveau, even if the speed isn't like that good as it should be, but you can do like real stuff with it. So coming to reverse engineering, there are like a few points or like some topics, different topics to reverse engineer stuff. For example, you have like this, like on CPU, you have an instruction set. And on the GPU, there are different versions of instruction set, actually. You have like those normal shader or CUDA cores, if you know what that is. If you don't know, it's kind of where all the graphic stuff is running on. If you, does anybody know, does anybody not know what GLSL is? Okay. So GLSL code is usually run on those processors. The Falcon Micro code, what's this F-mu-C stuff is standing for. It's usually like, there are some little co-processors on a GPU doing various stuff like context switching or power management or video decoding, accelerated video decoding, and they have their own instruction set. And we have like some tools to figure out, or at least to display what the hex code means, something like this. It's just to show you that, some colorful outputs. So you can if you have some code which is uploaded to the GPU, you can throw it to those tools, like if you're running the proprietary, the closed source driver, it's uploading some code to the GPU, and with those tools we can decompile and deassemble what's the code supposed to be. So it's, yeah.
Other names, as far as you know, made up names that match what you know of the instruction, or did you get information from NVIDIA?
The question is if we made up the names or get information from NVIDIA about this. It's kind of hard to tell, because if you have basic instructions like add or multiply, everybody's using the same names, really. There are some special instructions, but NVIDIA also has tools to decompile their stuff. So they have their own tools, and they are actually printing out their own names. So it kind of depends on the developer who's actually doing the reverse engineering work, if he is close to NVIDIA or not.
So the reason I'm asking is you may remember the differences in syntax between what was called GNU assembler syntax and Intel assembler syntax at some point, and it was really a mess. So I hope we can avoid it.
Okay, it's about the assembler syntax. It doesn't matter, because nobody will use it. So you won't write assembly code for the GPU. There's something like PTX for NVIDIA, but this is also a high-level language. It's not an assembly language, even if they sometimes call it an assembler and stuff like this. But it's not like C, but it looks like assembly code, but it's like real code, and nobody will target the low-level stuff, because on normal x86 architecture, you can use the same assembly code for all generations of CPUs. You can't do this on GPUs. So you would have to write your own code for new code for each generation of GPUs. So that's why it's kind of useless to think about having a stabilized assembly language here.
And maybe you'll cover that later, but is there a connection with the LLVM project? Do you use that?
The question was about connection to the LLVM project. No, there isn't. So we don't use it. It might be that we use it for higher level languages. There's somebody working on compute stuff, and it might be that if you're wanting to let your normal C code running through compute state, you might use LLVM to convert it to something we can accept. But directly, no. We usually use those assembly kind of languages for internal stuff. If there are internal shaders to do textures converting or stuff like this. So really internal stuff, we use something like this, but usually for the end user or for the developer, it doesn't matter. So. Okay. Another part is we also have a lot of different other devices on the GPUs, like sensors for power consumption or the current temperature and stuff like this. So there are also fans or voltage control, which are usually set through GPIO switches. Does anybody not know what a GPIO is, or the concept behind GPIO? Okay, I would say that GPIO is something like a hardware switch. It has two states, on and off, and you can either set the states or read a state. So if you have a voltage control and you have 16 steps, you need, you need 5 switches to kind of translate this number into an hex value. So you have 5 bits, and depending on which bits are set, you can set a value, for example. So it's like a bit, but in hardware, really. So, and I2C is just a hardware protocol to talk with devices. It's details doesn't matter. It just if somebody is interested, you can look it up, but I don't know the protocol and I never needed it. So they are just tools to use it and it's fine. We also have on recent GPUs or on high-end GPUs, there are also sometimes LEDs on the thing, and if somebody wants to have fun with it, we sometimes get some videos about happy users being able to do crazy things with their LEDs on the GPUs, like displaying disk activity and crazy stuff like this. So, yeah, kind of happy about this, the users. So now the more interesting thing, memory mapped I/O. Memory mapped I/O is kind of the idea you have a set of registers on your device, which are quite a lot, and you don't want to have like with memory mapped I/O, it just looks like some memory you have in your application. So it's a nice way to work with hardware, and you kind of use offsets and write values or read values somewhere, and this is kind of the concept of memory mapped I/O. The actual parts of the GPU are kind of mapped into this big range of memory mapped I/O region. I will show you later how kind of looks like if we do reverse engineering on this kind of area of the GPU, I say. There are various engines on the GPU, something like for displaying stuff, or the pgraph engine is there for rendering stuff. Like if you're doing OpenGL or OpenCL, it's going through this engine. There are also like this kind of video engines for accelerated video decoding and encoding. The PMU is like a small chip for power management, where you can if you don't want to depend on the host or the kernel to do stuff, like the kernel could crash or could be busy with other stuff, you can use this PMU to do various things like fan control or reclocking stuff, reading out temperature, raising alarms and stuff like this. So, and some tools we use for this is Mmiotrace. I doubt anybody heard of it. Does anybody know what the Mmiotrace is? Nice one. Okay. So, the Mmiotrace is kind of a handy tool, I would say, and I would like to see it used for more reverse engineering efforts in general. It's kind of if you have a closed source kernel driver and you want to know what this kernel driver is doing with the hardware, you can actually use the Mmiotrace to record all the accesses to the hardware from kernel space. It's a tool in the Linux kernel. It's upstream. Everybody can use it. It's usually also enabled on all distributions. And it kind of abuses page fault for its work. Does anybody know what a page fault is? OK, I see. So a page fault generally always happens if you want to access some memory, but it isn't there for whatever reasons. And so it has to be loaded from somewhere to be accessible for the application. What we do in the Mmiotrace is we kind of tell the module that nothing is there, so it page faults all the time. And the Mmiotrace is just a page fault handler to record what's the binary driver doing, and we can actually use it for seeing what instruction is actually executed on which memory region.
How do you deal with DMA regions? So if what you poke in the MMIO is just the DMA address and the actual commands or stuff are in some other memory region, how do you deal with that?
As long as it's mapped in memory, it goes through the page fault mechanism. I mean, you have like pages, memory pages, and the kernel or the MMU of the device is like responsible to tell the host that something isn't there. Like
that I understand, but let's say that you want to send a series of graphic commands to the card.
Mm-hmm.
One naive way would be to send it serially to some register, and that's easy to detect with an MMU intercept like this. Another way would be to set up a buffer somewhere with a list of commands in a region of memory that may be just allocated by a kernel and you don't know where it is, and then just poke the address of that buffer in the Mmio, so you would only see the address, and you would not know what's inside a common buffer unless you also know that you had to intercept the reads and writes to that region.
Okay, so the question was what's happening if like it's some buffer we don't have access to. So the Mmiotrace only maps memory regions which were like mapped through the IO remap call, if it's telling you something. It's a call to just map memory from devices into your virtual memory space. That's all the only hook we have for this.
So I think what you're saying from your answer is that it doesn't matter to understand what's going on.
Yeah, not really. So yeah, it doesn't really matter. I mean, if it's going through this interface, it will work. If not, then it doesn't. It's sadly currently only supported on x86 CPUs. There are some interest from ARM people to support it because sometimes if you still have like the open source code, the kernel driver could be written in a way that you really can't follow what it's doing. And this tool gives you a nice overview on what's actually happening on the hardware. And I have an example. I think it's not big enough for you, sadly. Can anybody read what's happening there? I mean, not like just visually. If you see like a few words, then it's okay. If you can't see it because you are too far away, then I'm sorry for this. So yeah, it's basically just on the left side, there's like a flag for read and write, some address, some value, and then we have like a database with documentation. And if we have an entry for this address, we can like print what was written there or read there. And this example, it's usually it's from a clocking sequence where the Nvidia driver is actually clocking an engine on the CPU and on the GPU, and we can like read out what value got written into what hardware register. Yes.
If I understand correctly, this is not direct output of Mmiotrace, but some tool which translates the output of the trace in serial form.
Yes, this doesn't show the output of the Mmiotrace. It's a tool to parse it. The Mmiotrace is basically just the white columns on the left side with the relative virtual address. So what the parsing tool is doing is it kind of reads the mapped region, subtract the base address. So we have just the offset to the device, and the value passed is this colorful thing. So, yeah. Okay. There's also something like you may have heard of it, the VBIOS. Who doesn't heard of the VBIOS before? Or that there's something like this? Okay. Okay, the VBIOS is more like a description of the GPU. There isn't really much code in it. Your system firmware requires the VBIOS to have some code for basic initialization of the display stuff. So just to display stuff, there's some code which is run on the host, but it's more like a pair of register addresses and values, so it isn't really doing much. But the important bits are there, like a lot of tables which are describing a lot of things. Like if you can imagine that most of the GPUs are in some way different. So some have different clocks, some have other fans or different combination, and also have different kinds of sensors on it. It's kind of difficult because each Nvidia GPU, even if they have like the same model name, they're still different in various things. And this gets all described inside the VBIOS. And what we have to do here is it's more like I say settings file for the kernel driver. And we actually have to figure out what all the bits in there mean and what the kernel driver has to do with the information it gets from the VBIOS. So there's a lot of guessing around, because if you have like the basic structure of the table and the basic idea of what it might be for, you can like, you have to make a good guess on what the function is, because you kind of have to see what the NVIDIA driver does differently after you change the bit or something. This can be usually automated, like imagine you can read out the fan speed, and there's a table for fan support, which is describing at which temperature you should like set which fan speed. And this can be like, you can change the video bytes, you can upload it to the GPU, the NVIDIA driver loads it from the system memory, and then something changed. And this you can record. So then there's also like software to be reverse engineered. The most important bits are like OpenGL or Vulkan, FortiBro for the video acceleration, and OpenCL and CUDA. Those are like the most important bits for the GPU our users care about anyway. So we kind of want to know what those user space bits of the NVIDIA driver are actually doing to the kernel driver or the hardware. So there's like a command stream or a list of commands which gets sent to the kernel driver to be uploaded on the GPU so it does stuff. And we kind of have to know what it has, what the NVIDIA driver do for various OpenGL commands or for various OpenGL shaders, so we can do the right thing in the end. There are a lot of isolated tests which can be run like from the command line. So we can really focus on one feature and see what's happening there. And we also have like a tool written against wall grind. We call it wall grind MMT. MMT, I think, stands for memory mapped something. I don't know what the T is really standing for. But it's like, it basically traces syscalls the user space does on the NVIDIA device files for speaking with the kernel driver, basically. So we kind of can parse what's happening there and try to get a better understanding. Any question about this, maybe? Because it's okay. Yeah?
So if you use these tools and reverse engineer some command stream and you figure out what the bits are, is NVIDIA fine with you uploading software, like upstreaming software that does the same thing and documenting?
Okay, the question is NVIDIA fine with us doing this thing? I was actually looking into some license agreement on NVIDIA stuff, and usually it's not allowed to reverse engineer or try to get the code of the tools they are using or their software, because we don't do this. We just get like, we have some input, this is our OpenGL shader or whatever, and then the output is the syscall. Because there's nothing, like, and you can't prevent somebody to trace a syscall user space is doing. So we are just getting this. We don't disassemble the tools or the user space of NVIDIA.
That's fine.
Yeah, that's like, I think clean room reverse engineering, we usually call this. So it's to really don't get into any legal problems with it. Okay. So coming a little bit to development, which is, I think, kind of weird, is that we have kind of an object-oriented kind of C style we are doing. glib is also doing some object-oriented C thing, and what we are doing in the kernel driver is kind of similar, although we are using like less macros for this, and it's usually just a table with function pointers. So we have like, if, for example, we have a reclocking subsystem in our driver, we can set different function pointer for different functionality for each chipset or each generation of GPUs. So we can share a lot of common code and just keep like the device-specific parts into their own files and own functions. So what we usually have to deal with on the kernel side is to implement various DRM APIs. DRM is direct rendering. I don't know if it's management, but it's not. But yeah, it's manager. I'm stupid. I can't read, but it's okay. Big part of it is implementing the KMS interface. It's like in the past you were actually, for example, setting the resolution of your display in user space or in the X server or something like this. So you had like your Linux console in a crappy resolution, but everything in X was fine in the native one. So with KMS, this kind of stuff got like moved into the kernel, and we do the mode setting, like setting the resolution and stuff like this in the kernel. And there's like RPs we have to implement for this. Access from user space, of course, like if the OpenGL library or something wants to do something, so it has to go through the kernel. There's also like memory management, because GPUs have their own kind of memory, and it has to be somehow managed. If you have like 1 GB of video RAM and you actually need like 2 GB in your OpenGL application, then you have to like have some parts in the system memory and some parts of the video memory, and the kernel driver has to deal with it. And of course, there's also like rendering, which is kind of the same, like getting commands from the user space and just setting some commands on the GPU. Then the hardware monitoring interface we also implement in the kernel, and the power management stuff I talked before. Okay. Then there's, of course, also the X11 part of software, which is just for basic 2D hardware acceleration. I never got in touch with doing anything in there. It's mostly just for getting something to display on the X server. So if somebody's interested in this, I'm not. So. And one of the most important bits is like the Mesa library. It's an open source OpenGL implementation. It's there for implementing all the hardware acceleration stuff. If you're doing like video decoding or graphics acceleration, it's all in there. We also have a big shader compiler there. So we have a real compiler which is doing is a SSA-based backend compiler. SSA is a static signal assignment. This is a concept that each variable can only be assigned once. And this makes a few compiler stuff things much easier. And if you are like interested in working on a compiler, this would be a good idea because we have a lot of things to do there. For the bow, of course, for the video acceleration, OpenGL is currently kind of a work in progress project. Some student is working on this. And if somebody is interested, could help out. And of course, Vulkan is also a to-do list, which I hope it will be done this year. So. 5 minutes. Yeah. For OpenGL, I think the biggest. I try to skip now little things because I want to talk about something else as well later. The biggest item currently is like this Kronos conformance test suite. It's like to verify that our OpenGL implementation is really doing the stuff it should do. So if you're aware of the basic concept of OpenGL, then there are also extensions, stuff like this. So what's this kind of a not so big part in our work, which should be a little bit bigger, is working together with Nvidia. They're kind of protective about a lot of stuff. So they open up a little and provide basic documentation for basic features, which is like display stuff. So they kind of help us with this, but it's more like they gave us some files which are in public with names and registers, and that's kind of everything we get on this side. So we still have to figure out a lot of stuff. We don't know in which sequence we have to set something. So, but it kind of helps for a new generation of hardware because we don't have to search for all this stuff. There's also an open source Android driver which got actually replaced by Nouveau on some devices. I think the Pixel C is called. It actually, there was an official Nvidia beta version, I say it, where they actually shipped Nouveau. And we are working with Nvidia to get signed firmware for those little co-processors on the devices, and they are needing a lot of time for this, but at some point they actually release it, and then we can start doing stuff also on those newer GPUs. Okay. Current challenges, of course, exposing higher level of OpenGL, improving performance, which most of the users care about, because if most of the time saying, yeah, Nouveau has crappy performance, I rather stick to NVIDIA even if it's closed source. We actually want to build up a CI system because currently there's like no automated testing at all. There's some software written at Intel to do automatic GPU testing, but still need time to set it up. On Maxwell 2 generation, there's like this problem with the signed firmware stuff, also with the signed video BIOS, where we can't change things and we can't upload our own code or own video BIOS or whatever. And this is like really killing reverse engineering on those hardware, because if you can't run your own software, there's nothing you can really do or implement or figure out yourself. So it's a little bit troublesome. And of course, compute support, which some people care about. So, yeah. And if you want to help, it's most of the time a good idea if you just own NVIDIA hardware and it has bugs running Nouveau, and you are kind of interested or motivated to just fix those issues. I started like this, and it worked out quite well, so maybe somebody of you will as well. And of course, it's also important to be interested and motivated. And for students, there's always the chance to just do like a Google Summer of Code project or Endless Vacation of Code, which is an XORG Foundation kind of thing, where you get basically paid to work on open source projects. And usually we also always have slots for students to work on projects for this. So this is, I think, a good thing for students. So and then I'm done. Some links if you are interested. We have an IRC channel, mailing list where you can just dump questions to, and some Trello boards with to-dos. That's all. Any questions? Yes.
That is broken with KDE. I mean, with the composite on Kiwi, you see lots of errors graphics. So why don't Fedora uses the Nouveau driver as default as upstream suggests?
Okay, the question was that the mode setting X driver seems to be broken on KDE. And the question is why we don't use the Nouveau one on Fedora by default. So there's a difference between the X driver and the kernel driver. If you use the X mode setting driver, you still use Nouveau kernel driver. It does hardware acceleration in a different way. It's using OpenGL to do the hardware acceleration. So I'm not quite sure about the main reasons, but I think somebody wants to, or there was this idea to use the mode setting driver for all hardware. And this is basically the reason why it's the default one. I don't think there is a real deep technical reason besides reducing maintainership. Like if you only have one driver for all devices, even for Intel and AMD, then you don't have to maintain 3 different projects for, yes? Other questions?
Can you use just a driver firmware from Nvidia?
The question is if we can't just use the firmware from Nvidia. We do it for video acceleration because nobody really got to implement our own firmware for this. Usually we write our own firmware. For the sign firmware stuff, they kind of hide the firmware really deep inside the driver, and we don't know where it is. So if somebody would work on getting those firmware files, yeah, we could add support for those, yes. Okay.
Just checking whether the connector for the clicker is here or there.